Hello and welcome everyone to week 12 of the NPTEL live session for the course of Foundations of Cryptography. This will be the last live session for this course of this semester. So, because of the fact that we already had discussed all the topics of all the weeks previously, so and also the corresponding questions that were posted on the NPTEL website. So today, because this is the last class and after a few days, you have the exam also for this course. So I will just discuss a broad overview of the whole course. Also, as you know, this is a very vast course. So in 2 hours, I will try to cover just to recapitulate whatever was done in this course, and mostly with the stress on symmetric cryptography, because that was covered quite a few weeks ago, and the public key cryptography topics were covered recently. So I will just keep more stress for recapitulating the symmetric key part. Okay, so let me start. And this is just a handwritten note. I did not make slide for this session for the overview of the whole course. So this will be a handwritten note. I hope you will be able to understand. Okay. So let me proceed. So basically through cryptography, what we generally want to achieve is that three main objective of cryptography is privacy or confidentiality of data. So data is being communicated over public channel. So you need to maintain confidentiality of that data. And second is integrity. That is, while being communicated, data should not be perturbed by any malicious party. Even if it is changed midway, then that change should be detected, that well, whatever message we have received, that is not the exact one that was sent from the center. And the third point is authentication. That is, whoever is the sender, like I am receiving a message and I am seeing that some party A has sent this message, and to verify that it is indeed party A who generated that message and sent to me, that part is ensured by authentication. Okay. So to achieve these three goals, so basically there are several notions of security. There are perfect secrecy that was initially introduced in this course. Then we also talked about information theoretic security when we discussed information theoretic secure MAC or one-time map. We will come to that. And then also we discussed about computational secrecy. So perfect secrecy is something which is, as you know, perfect. So in practical, nothing is actually perfect. So it is just a theoretical concept, and it's defined as when we talk about perfect secrecy while communicating message in encrypted form, then we say that we allow the adversary to have computationally unbounded power. Okay, so it has no bound on the computation, so it can do any high level of computation that it requires. And we also say that even if with that computationally unbounded power of that adversary, the adversary should not be able to gain any meaningful information by observing the ciphertext. So basically here we talk about ciphertext only attack, or like for a passive adversary who just observes the ciphertext being communicated over a public channel. So does it gain any information by seeing the ciphertext? So our aim is that whatever prior information about the distribution of plain text the adversary has, it should have exactly same information even after seeing the ciphertext. So the ciphertext should not leak any extra information about the distribution of the underlying message. That is what we denote by this equation, like probability of capital M equal to small m upon the fact capital C equal to C. So capital M is a random variable and capital M equal to M means that while encrypting, so the message being encrypted, the probability that message being encrypted under the ciphertext small c is actually small m. That is the probability. And the right hand side says the just among the message space, exact probability of small m to being chosen as the plain text. So that is the a priori probability that m could be communicated, any small m to be chosen from the message space, and this is posteriority probability, and that is inside ciphertext C exactly message m is encrypted. Okay, so these two probabilities should be same, which also means that seeing ciphertext C, we cannot gain any extra information that which small m is encrypted under C, right? And this same thing also can be represented as probability of capital C equal to small c, while the underlying message m is m0 is exactly equal to the probability of capital C equal to C, while the underlying message is M1. So this is the same thing expressed in two different ways. You have already seen how we can prove from the first relation, the second relation, and from the second relation, first relation. So we can prove them in alternative manner. Okay. So now, this exact concept of perfect secrecy, that adversary does not know anything about the underlying plain text, can be represented in the form of a game between challenger and adversary. So you have already seen that whenever we define some crypto primitive, so we first define what we want to achieve through that crypto primitive. That is the formal definition of the primitive, and then we instantiate with some exact algorithm of that construction, and then we provide proof of security for that construction, that the construction indeed is able to achieve the notion of security that is defined in its formal definition. So anyway, here in case of perfect secrecy, we define the game as seen in the diagram. So here is the challenger and here is the adversary, and adversary provides to challenger two messages M0 and M1 such that they too have same bit length, and then challenger arbitrarily chooses any one of them. So let's say B is the bit chosen. So if B is 0, then it will encrypt M0, and if B is 1, it will encrypt M1 under this CB, which is sent to adversary. And after seeing this challenge ciphertext CB, adversary has to guess what is the underlying message encrypted in CB, whether it is M0 or M1. So it needs to guess the bit B dash. Okay. So the perfect secrecy requirement says that the probability of adversaries winning, that is, it is actually able to detect or guess the bit B dash. So B dash equal to B, that probability is exactly half. Why half? Because anyway, by random guessing, so there is only two possibility of the answer B dash, right? 0 or 1. So any random guess is able to give the correct answer with probability half. So adversary should not have any extra advantage in that guessing work. So the probability that B dash equal to B should be exactly half. So that is it. So this is the concept of perfect secrecy that we initially introduced. Right now, from perfect secrecy world, so there is an example of perfectly secret encryption scheme, right? So the example is called one-time pad or OTP. In OTP, we assume the message space, key space, and ciphertext space, all the three spaces to be exactly same, that is 01 to the power small l, which means the space consisting of all L length binary string, right? So you have binary string, that is 01 string of length L. Now, you will encrypt some message M from this Mohan Sai, you raised hand. You want to ask something?
Ma'am, is there any previous year question papers is there, ma'am?
Sorry, is there any? I did not get you. Please
Previous
come
year
again.
question papers for external exam.
Uh, I actually don't think so. If we have previous year's question available with us, I don't know actually.
Okay,
Okay.
ma'am. Thank you.
Okay. So, okay. So let me continue. Now, so how do you encrypt in one-time pairs? That is, you have your message M from this space 01 to the power L, and key is also from the same space. So for encryption, you just do M XORed with K. So you have M also as L length binary string and K also as L length binary string, and you just bitwise XOR them to get the ciphertext C. And while decrypting, accordingly, you have the ciphertext of L length binary string. Key is also from the same space. You just do C XOR K. So your C was M XOR K. With that, you XOR K again. So you are just left with M. That is how decryption works. And if you just notice that given a ciphertext C, there is exactly same probability of being the underlying message to be some particular message from 01 to the power L space, right? So for each possible key of this space, there will be a different message which can be encrypted in C, right? So that is why we say that the scheme is perfectly secure. However, the scheme, the whole notion of perfect secrecy as well as this particular example OTP has some limitations. Like the key is as large as the plain text, right? So if you want to encrypt some 100 bit of message, you need key also of at least 100 bit. Otherwise, you cannot perform bitwise sort, right? So key should be as large as the plain text, and also you cannot reuse a key to encrypt several messages at a stretch, right? So uh, so basically to overcome these two limitations, okay, why you cannot reuse a key? Because if you just encrypt two message M1 and M2 with the same key K, then you can actually obtain C1 XOR C2. That is, sorry, you can obtain actually the information M1 XOR M2 by doing XOR between the two corresponding ciphertexts C1 and C2, right? So you will have some partial information about the underlying message like that. So you cannot reuse the key. So anyway, to overcome these limitations, actually we introduced the concept of computational secrecy, which is applicable in the real world or modern cryptography. Okay. But before going to computational security, I would just like to mention that in case of information theoretic security, there also you assume the adversary to have unbounded computational power, but there we allow the adversary to win with negligible probability. In case of perfect secrecy, your adversary will be computationally unbounded, and your adversary uh, is never able to win the corresponding security game, not even with negligible probability. But here in case of information theoretic security, we allow the adversary to win with negligible probability. And in case of computational secrecy, your adversary will have computationally bounded power or bounded computational power, and then adversary also may win with negligible probability. Okay. And by allowing these two relaxation, we actually able to achieve shorter key size and reusability of the same key. These two limitations were there with perfect secrecy, but by relaxing the adversary power and probability of adversaries winning, we could achieve this practical scenario where we can actually use this cryptographic schemes, right? So just to mention, we just uh, get this concept of negligible probability again and again throughout our whole course. So what is negligible probability? or what is called a negligible function. So we call a function f of n to be negligible function in n if for all pn, which is nothing but some polynomial function pn, okay, for all polynomial function pn, there should exist some capital N such that f of n is less than 1 by p of n. So, there should exist at least some n, capital N, for which the value of fn should be even less than the inverse polynomial. So Pn is the polynomial, 1 by Pn is the inverse of that polynomial, and Fn should be even smaller than that. And that is when we call that function Fn. Call that function Fn negligible. Okay. For, of course, you find the capital N, and then for all natural numbers small n greater than capital N, this condition should satisfy. Okay. So, okay, now just to recall again, we have seen various kind of attack models for our encryption scheme. We have seen ciphertext only attack, where the adversary is just acts as an eavesdropper, and it is passive in nature, so it does not try to uh, just it does not try to perturb the message. It just silently observes and try to gain some information about the underlying plain text. Okay, that is the scenario in ciphertext only attack. And there is also one concept of known plain text attack. Here, the adversary actually sees more than one plain text ciphertext pair. However, the plain texts are not chosen by the adversary. So it just randomly could find some message ciphertext pair. Okay. And in case of CPA, adversary actually has more power, and here adversary can choose message of its choice, and it has an encryption oracle access such that for its chosen message it can see the corresponding ciphertext. And in case of CCA, the adversary has been even more powerful. If, apart from the access to encryption oracle, it also has access to decryption oracle, where it can provide ciphertext of its own choice and get to see the corresponding underlying message. And there is one restriction to use decryption oracle, that is, the adversary, after seeing the challenge ciphertext, so if you remember the game of semantic security, right? So there, the adversary provides the challenger with two messages M0, M1, and in response, the challenger gives back to the adversary encryption of any one of them, either M0 or M1, and adversary's job is to distinguish between encryption of M0 from encryption of M1. But this task, in case of CPA game, the adversary is provided with an extra access of encryption oracle, and in case of CCA game, the adversary is provided with the extra access of both encryption oracle and decryption oracle. But while using the decryption oracle, after seeing this challenge ciphertext C, which can encrypt either M0 or M1, the adversary should not query the decryption oracle with the challenge ciphertext itself, because in that case the adversary will trivially win and there is no meaning to the game. So apart from the challenge ciphertext, the adversary can access decryption oracle by querying with any other ciphertext. Okay. So those are the concepts of various attack model. And about the game, just now I said that indistinguishability based definition of semantic security for these three models: COA, ciphertext only attack model; CPA, chosen plain text attack model; and CCA, chosen ciphertext attack model. Is this a revision? Yes, this is a revision because we already covered the last few weeks topics, right? So this is just, you have, I guess, exam on 28th or 29th. So this is just trying to give a broad overview of the whole course, right? Obviously, it's not possible to give all the topics covered in these 2 hours, but I will try to just go through them in a very broad manner, okay? So, okay, so this is, I just talked about this, right? Okay, so in the So as you see, in case of COA model, just 3 round of conversation is there. And in CPA model, there is the access to encryption oracle, both in a pre-challenge phase and in a post-challenge phase. What do we mean by pre-challenge and post-challenge? That is, there is some phase where adversary is giving the challenger M0 and M1 and in return getting back encryption of any one of them. That is the challenge phase, right? So challenger is challenging the adversary that tell me which encryption you are seeing. So that is the challenge. But before challenge, the adversary is allowed to access the encryption oracle, right? And after challenge also, which is the post-challenge query phase, there also adversary is able to access the encryption oracle in case of CPA model. And in case of CCA model, in the pre-challenge and post-challenge phase, both the cases, it can raise in encryption query and as well as decryption query, right? So that is what is being shown in this figure. Okay. And also this notation that probability b dash equal to 1 on b equal to 1 minus probability b dash equal to 1 on b equal to 0, this should be negligible. That is, your whatever challenge ciphertext is encrypting inside it, be it M0 or M1, that is B is 1 or 0, irrespective of that, the adversary will detect B dash, which is the guessing bit by the adversary, that should be 1 with almost similar probability. Okay, you can replace this B dash equal to 1 in both the expression with B dash equal to 0 also, right? So anyway, whatever be the input B is, right, B dash should be similar in both the cases. Probability of B dash being 1 in both the cases should be almost same. Okay, so that is why we say that this probability difference is negligible. Okay, so further proceeding, so there are main two primitives, right? Symmetric cryptography and asymmetric cryptography. Maybe you already remember, just to for the sake of completeness, I should mention that in symmetric cryptography, both the sender and receiver are communicating with each other using the same key at the both end, encrypting end and decrypting end. On both sides, the same key K is used. And in case of asymmetric cryptography, the encryption end key and the decryption end key, they two are different. So there is concept of public key and secret key, as you have already seen. Okay, so there are some symmetric key primitive. Hash function is not like it can be used in both symmetric and asymmetric key. It has a broad application area, and all of them are actually used together to get efficient and secure crypto primitive in real world, right? So okay, I will just touch or will try to touch these topics. So let us just recap what is PRG. So it is pseudo random generator, right? So pseudo random generator is well, there is some marks on the screen. Yeah, so, thank you. So in case of PRG, right, you have this, it's a efficient deterministic algorithm. Okay, so you will be provided with some seed. So seed is obviously secret. Seed is the secret, and the PRG algorithm will take as input the seed, and it will output a bit string which is whose length is necessarily whose length is necessarily greater than the length of the seed. Okay, so expansion is necessary in case of PRG. And why we need PRG? Because we need in the real world, actually we need in various cases random numbers to be generated. But because truly random number generation is a very costly process, that's why we move to pseudo-random generation, where the bits are not really random, but it looks like random. Okay, so that is where the application of PRG comes. And so the security requirement of PRG is its pseudo-randomness, that is, output should be indistinguishable from uniform random element of 0, 1 to the power L, I have written. So capital L, you can think of the PRG to take as input seed of length small l, and it is outputting the a bit string of length capital L, such that capital L is greater than L, strictly greater than small l. And so the output should be indistinguishable from uniform random element of the space 0, 1 to the power capital L. Okay, so the game we define like this. So there is again challenger and adversary, and challenger in the setup phase of the game only, it just decides by tossing a coin whether it is going to provide the adversary with a PRG output or with a truly randomly generated output of bit length capital L. Okay, according to that, challenger provides Y, whereas Y can be generated in any one of the two methods. And the adversary's job is to guess whether it is seeing a PRG output or a truly randomly generated output. So that is the guessing bit B dash. Now, adversary wins if B dash is equal to B. That is, adversary is correctly able to guess whether it is seeing a bit string which is generated by PRG or which is generated by truly random generator. If adversary wins, then of course the PRG construction is not secure. So we say that this probability should be equal to half plus negligible. Half is the by default, through random guessing, the adversary should be able to guess the right bit B with probability half, and apart from that, it should have just only negligible probability of winning the game. That is when we say if this condition is satisfied, that adversary's winning probability is half plus negligible, then only we say that the PRG is secure. Okay, so we can use PRG in case of stream cipher. So we just discussed OTP few minutes ago. So in OTP, that which achieves perfect security, there actually we used to encrypt message by doing MZOR K, where K is a randomly generated key string which has the length same as M, right? So we needed the key to be as large as the message in case of perfect security, but we said that that is not practical. So every time we won't have the key length exact same as message length, because for that we need to know the message beforehand, right? So which is not the case in real life. So here is the solution, that you will have a key of fixed lengths, say small l, but whenever you have capital M of some length capital L, then according to your requirement of the value capital L, you can use your PRG, your pseudo-random generator, using the key K, and then get a capital L bit string, and then you use that key string just like OTP. So you do MZOR G of K. Okay, and decryption also happens in the same way. So here the security of this stream cipher directly depends upon the pseudo-randomness of underlying PRG capital G. And this is actually deterministic encryption, as you can see, because what is deterministic encryption and what is randomized encryption, by the way? So we say any process, actually not only of encryption, any algorithm which makes use of some randomness or some value which is generated with some from some probability distribution. So if there is this randomness involved in some algorithm, then that algorithm output, so that algorithm, we say it's randomized algorithm. Or in other words, if you there is some algorithm in which you give input the same value every time, but you are able to see different outputs each time you run the algorithm with the same input. Okay, so then the algorithm is actually randomized algorithm. But what is deterministic? Then every time you feed the algorithm with same input and you are bound to see the same output every time. That is what deterministic algorithm. Now, in case of encryption also the same thing applies. So in case of encryption, if you have a deterministic encryption process, then the encryption scheme actually does not satisfy the concept of multi-message security or and also CPA security. Okay, why? Because if there is no randomness involved in the encryption, then if first time you encrypt a message M and see the ciphertext C, okay, and next time also whenever you see the ciphertext C, you actually know what is the underlying message M, right, which is not desired. So every time you encrypt M, that should map to some C1 C2 every time using some internal randomness of the encryption algorithm. Okay, so because the stream cipher does not have any you remember that PRGG is a deterministic algorithm, right? So overall in the encryption process, there is no randomness involved. So this is not multi-message secure, this particular stream cipher, okay? Next, we move forward to another crypto primitive, which is the very basic crypto primitive of the whole symmetric key world, which is called one-way function or OWF, okay? So one-way function, as the name suggests, that it's one way, right? From the domain, say capital X, to the codomain or range, capital Y. So it is easy to go from X to Y, but not the reverse way. So coming from Y to X is not easy. So to say it formally, say small f is a one-way function which maps any length of 0, 1 bit string to any length of 0, 1 bit string again. So then there is challenger and adversary, and challenger samples some input X from its input space, okay, and then it computes the value of Y by doing f of X, and it sends to adversary the value of Y. By seeing the value of Y, that is the functional output value corresponding to X, the adversary's job is to guess some X dash such that f of X dash is equal to Y. Note that it should not be exactly equal to X, because the function may not be 1 to 1. It can be many to 1 also. So given Y, the adversary has to guess the any pre-image of that value Y, right? What is pre-image? Because any X, okay, for which fx is equal to Y, then we say that X to be a pre-image of Y, right? So the adversary has to guess any such pre-image of Y given Y, okay? But this job should be hard for the adversary. So formally we write that probability that f of X dash is equal to Y should be upper bounded by a negligible function, okay? By the way, if this Zoom meeting ends, you can join the same link, okay? Right. So this is what the concept of OWF. Now there is a related concept of one-way permutation. So if you just replace this domain and range in such a way that this function becomes bijection. Bijection means 1 to 1 and on to, right? So each input from the set X or from the domain X should map to exactly same output in the set Y, okay? Then that function is called 1 to 1, and on to means all the elements in the set Y should have exactly one and unique pre-image in the set X. So that is what is bijection. So if a one-way function is actually a bijection from the set X to set Y, then we call it one-way permutation. So that is what I just said. Each Y in each small y in the set capital Y has unique pre-image in X. So next we just recapitulate another concept which is called hardcore predicate. So basically OWF, as we said, that given Y, it is hard to compute X in its entirety. So exactly X should not be recovered from Y. That is okay. But that does not say that you should not have any information about the input x. So you can gain some partial information about the input x that is allowed in one-way function definition. So we just exploit that fact only in the concept of hardcode predicate. So it says that given any function f, we call a Boolean function denoted as HC for hardcode predicate. So HC, which is mapping any length of bit string to some Boolean value 0 or 1. So it is a Boolean function, this hardcode predicate thing. This is Boolean. So HC is called a hardcode predicate if given x, HC of x is computable in polynomial type. So computing HC of x is easy, but given fx, okay, for any random x, then HCX is not computable in polynomial type with probability significantly better than half. Why this half comes? Because HC is a Boolean function, so guessing its output, whether it is 0 or 1, that exactly has this probability half for random guessing. Apart from that, we just allow a very negligible probability of guessing HCX. Okay. Now, so I just said that in case of OWF, seeing the output Y, it is hard to guess the input X in its entirety. And there is some part of X which can be guessed by seeing Y. Okay. And also there is some part of X which cannot be guessed by seeing Y. So which cannot be guessed by seeing Y, that part only we call it hardcode predicate, right? So seeing fx or y for any random x, HCX is that part which cannot be computable in polynomial time or cannot be guessed significantly greater than with probability half. Okay. That is what it is showing formally. So y equal to fx is provided to adversary, and adversary is trying to guess the value of HC of x because HC a Boolean function. So it is outputting some bit b belonging to 0 or 1, and the probability that HC of x is actually the bit guessed by the adversary, which is b, that probability is upper bounded by half plus negligible. So that is the concept of hardcode predicate. Now, how this hardcode predicate comes to use? So here you see that there is Goldrick-Levin theorem, GL. Okay, so this theorem actually proposes that if one-way function exists, then you can construct hardcode predicate from one-way function. But this construction is not directly straightforward. So for any OWF, it's not proposing hardcode predicate for that OWF only. Rather, given f, which is a OWF or OWP, one-way function or one-way permutation, it first construct another function g, which is also OWF, provided f is a OWF. So how g is constructed? So g is a two-input function constructed as g of x comma r equal to fx comma r. So fx is the OWF and r is exactly output. So let's say x and r both have bit length n. So the last n bit of the input is exactly copied in the n length last n bit of the output. And fx, let's say if it is a one-way permutation, then x being a n-bit string, f of x is also n-bit string. So seeing the first half of the output, guessing anything about the first part of the input is impossible. Although some information about the whole input to g, which is x concatenated with r, so the information about r is easily available by seeing the output of g of x comma r. But this part of the input, which is first part of the input, the information about x is hard to compute. Okay, so g is also one-way function because from x to r it is easy to compute fx comma r, but from fx comma r it is not easy to compute the whole value of x and r. Okay, so g is a OWA provided f is a OWA. And what is hardcode predicate here? hardcode predicate is given as some random subset sum of the value x. So you choose some bit. So you actually perform R1 x1 XOR R2 x2 and so on till Rn xn, where both x and r are n bit vector. So you basically, if you treat x as n bit vector and r as n bit vector as well, or I mean vector of size n with each element being 0 or 1, okay, then you apply dot product modulo 2, then you whatever quantity you get, which is all of course 0 or 1, so hc is indeed a boolean function here, then it is hard to compute. Okay, that is the proposition by Goldrake-Levin. So given a OWF or OWPF, you first construct another OWF or OWPG, and for which you propose hardcode predicate HC, but it is not direct construction from F. So on the belief that OWF exists, then you can propose this construction of hardcode predicate. Okay. Now, once you get hardcode predicate from OWF, then you also proceed to, let's say, constructing PRG from OWP. Okay. So this construction is like this, that you are provided with some OWP F, okay, mapping n-bit string to n-bit input string to n-bit output string, binary string, and then let's say hardcode predicate for this function f. So the way Goldrake-Levin theorem proposes of having hardcode predicate for some OWP, like that, you, let's say you have come up with this function f, which is a OWP, and its corresponding hardcode predicate, which maps its input to some Boolean value 0 or 1. Then you construct a PRG G of S as f of S concatenated with HC of S. Now, because it is f is a one-way function, so from the value of f of S, you cannot guess S, that is ensured by the security of OWF or OWP. And also because HC of S because HC of S is indistinguishable from any random bit 0 or 1. So by seeing the value of HC of S also, you cannot guess anything about the underlying seed, and you cannot actually distinguish this whole string f is concatenated with HC of S from any uniformly random string of the same length, that is n plus 1. Okay. So so that is how we construct PRG from OWP. Next, we see once we are done with having PRG from OWP, having expansion length ln equal to n plus 1. So from n bit input, you are getting output of n plus 1 length. Then we proceed to having PRG with polynomial expansion, right? So for L of n equal to some poly of n, polynomial function of n. Okay. So how that is achieved? So let's say you want to achieve from n bit length input, you want to achieve n plus n length bit output. Then you can actually apply sequentially the PRG algorithm to your repeatedly to your available seed. Okay, so let's say seed which is from n bit length binary string. You first apply S to G and you get n plus n length bit output. So your first n bit are provided to next PRG algorithm again sequentially. So let's denote it as S1, and last bit which we denote it as R1. Okay. So this R1 is considered as part of the output, and again this in-bit length output is fed to this PRG block G, and S2 is output as the first n-bit length string, and the n plus 1th bit R2 is returned, and like that, so on. It goes on till capital L times, so that we actually get R1 to RL, capital L number of uh, extra bits in the output, and then the final SL, which also has the bit length of small n. Okay, so like that, the whole output of this whole construction, which we denote it as G dash. So the G dash of S consists of R1, R2 to RL and concatenated with SL. So like that, you receive PRG with polynomial expansion. And then let's talk about practical instantiation of PRG. So whatever we had seen here, the concept of OWF, then constructing hardcode predicate from OWF, and constructing PRG using this hardcode predicate, and constructing PRG with minimal expansion, PRG with polynomial expansion. All these are actually probably secure instantiation of PRG. So all these are theoretical concept, but in real world application, all actually getting candidate for OWF, all these things are not real. So you need practical efficiency for real world implementation, and for that you actually deal with LFSR based PRG. LFSR is linear feedback shift register, and those are not provably secure, but they are heuristically secure, which means I'm not talking about exactly LFSR based PRG, but there is several variants of LFSR based PRG where those constructions by several years of effort to attack those PRG, that is breaking the pseudo randomness of those PRG. So that effort has remained unsuccessful. So we believe those constructions to be secure in practical world. Okay, but they are not based on some assumption or some existence of some underlying primitive like OWF or something. So those are not probably secure, but those are believed to be practically secure. Okay, so so in practical instantiation of PRG, we actually abstract it with two algorithm. First is init, where it takes the seed S and an optional initialization vector IV to output an initial state ST0, and then you run get next bit multiple times for however number of bits you require in the output. So it takes current state STI and moves to next state STI plus 1, and it outputs a bit YI plus 1. Okay. So anyway, next concept that we just recapitulate is the concept of PRF. So it is pseudo-random function. In case of PRG, we just generate pseudo-random bits. Okay. In case of PRF, we try to simulate the output of a truly random function. So depending on two distinct input x1 and x2, their corresponding output should be independent of each other and should be distributed uniformly over the output space. So that is how truly random function behave, and the similar functionality we expect from pseudo-random function. So this is deterministic function. It's skewed function because it takes as input both an input x, and also it makes use of some internal secret key k. Okay, so until that key k is secret, we expect the output of that pseudo-random function to remain indistinguishable from output of a truly random function. Okay, so the game is defined like that. So your f has key of bit length n, input has length small l, and output has length capital L, and your challenger here decides in the setup phase only whether it is going to provide the adversary with PRF output or truly random function output. So according to that, it just tosses some coin and gets bit B. And depending on value of B, it either provides the adversary with Fk of xi for each input query xi, or it provides yi, which is a truly random function output on the input xi. Okay, and by seeing several such yi corresponding to xi's, it has to guess whether it is interacting with a truly random function or a pseudo-random function. That is adversary's job, and it accordingly outputs some bit b dash, and adversary wins if it is able to correctly guess the bit b. That is, if b dash equal to b, and that probability is upper bounded by half plus negligible in case of a secure PRF. Okay. And there is similar concept of PRP or pseudo-random permutation. So it is a PRF which is a bijection again. So your input bit length and output bit length should be exactly equal. So every PRP is a PRF, but not every PRF is PRP. That is trivial. There is also another concept of strong PRP. So we say that adversary is given access to inverse of the function or permutation. So basically, what is the difference between PRP and strong PRP is that in PRP, the adversary is allowed to query with xi to the challenger, and in response, it is allowed to see the corresponding PRF evaluation for those input xi's. But in case of strong PRP, the adversary is also allowed to query the challenger with some yi's of the output space and get back the corresponding xi's such that xi is f inverse of yi under the secret key k. Now, the adversary's job is again to distinguish between PRF output and truly random function output. Okay. So the game is exactly the same, just adversary is more stronger here because it has the access to inverse oracle of the function. So that is strong PRP. Now, just for recapitulation again, we will visit the how to construct PRG from PRF. So you were given a PRF F, which takes as input small n length key and the small n length key and small l length input, and gives output of length capital L. And you have to design a PRG which takes as input a seed of length small n and will output some bit string of length small t cap into capital L such that small t is polynomial function of n. Okay, so basically output with some polynomial expansion. Okay, so the construction is simple. You apply parallelly the PRF on the input 1, 2, so on till t, using the PRF key as the seed to the PRG. So the PRG you are going to design, you use its seed. So you feed as its seed the key to the PRF. Okay, and then you use that key to the that same key to several instantiation of the PRF in parallel, and all these PRFs takes as input 1, 2 to till t. Okay, so like that you give as result output y1 concatenated with y2 till yt, and each of yi is nothing but fk of I, where k is the key of the PRF. Okay, and again its security or pseudo randomness of the PRG depends on the pseudo randomness of the underlying PRF. Okay, and also there is the construction of PRF from PRG. So here you actually use Goldwasser-Micali construction. So this is a tree construction where you make use of some length doubling PRG, which takes a seed of n length bit string and outputs 2n length bit string. And you want to design some PRF whose key has length n, input has length n, and output has length 2n. So basically, the seed of the PRG is used as the key of the PRF. Okay, so the construction goes on as follows. So you first compute G of K. G is the PRG and K is the seed. So you compute G of K to get 2n length bit, 2n length output. The first half, which has n bit length, denoted as K0, and the second half denoted as K1. Then depending on the bit value of 0th position of your input, you either go to left or go to right. Okay, so if your leftmost bit is say xn minus 1 is 0, then you go to left and you apply the PRG again on the first part of the output, that is K0. And if the leftmost bit is 1, then you go to right and you apply the PRG on the second half of the output, that is K1. Like that it proceeds, and it will have, the tree will have a depth equal to n, that is the length of the input. Okay, so like that it proceeds. So the finally, basically in the leaf node, you actually have say 2 to the power n number of leaves, each corresponding to one of the 2 to the power n value of input. Okay, your input has length n, so you will have 2 to the power n possible values of inputs, and each of the leaf actually will denote the value of PRF with the same key K on input of that 2 to the power n different input streams. Okay. Next is construction of PRF to PRP. So you are given with some PRF and you want to get a secure PRP from that, and for that you actually internally use some construction called Feistel network. Okay, so Feistel network in general is a method to construct invertible function from an arbitrary collection of functions. So these functions need not be invertible, they can be and neither they need to be PRF or something, but we will use this network for our construction of PRP from PRF. So in general, Feistel network behaves as follows. So let's say you are given with two functions f1, f2, each mapping some n bit input to n bit output, and you want to design invertible function capital F, which maps 2n bit input to 2n bit output. Okay, so let's denote the input as 2 half. So your input length is 2n, so you divide it into 2 half. First half denoted as L0 and second half denoted as R0, and your Feistel network will consist of 2 rounds here because of these two functions. So you after applying first round, basically this R0 will come as it is as L1. So your L1 is equal to nothing but L0, and your R1 is constructed as L0 XORed with F1 of R0. So you apply your function F1 here, and like that you get the first stage intermediate output. Okay, and then the final output will be computed as again R1 coming to L2 as it is, and L1 XORed with F2 of R1, that coming to as R2. Okay, and you can show its invertible property very easily by going back. You can actually get back to this X because of the way this each step of Li and Ri are defined to be constructed from Li minus 1 to Ri minus 1 of Feistel network. So for this pattern of construction, it is always invertible. Okay, so now for constructing PRF from PRP, you can actually make use of this network. So you are given a PRF of key length n, input length n, and output length also n. Now your PRF will be actually having key length of 3n and input length of 2n and output length of 2n. So again, similar kind of design will be there. Just only difference will be that we have only one function f instead of here there were two function different f1, f2. So here we have only one function f, but your PRP has key of length 3n. So you basically use the key as three different key each of length n, and you use f of k1, f of k2, and f of k3 as three different functions because the keys are different. So you will use fk1, fk2, and fk3 as three different function in three round fiscal network, and thus you will achieve or you will able to construct a PRP, okay, from your PRF, okay. And also, if you want to construct a strong PRP, right, for constructing strong PRP, you have to apply the fiscal network for 4 rounds, and of course your key length will be of length 4n then, okay, right. So now we will proceed to this message authentication code, okay. So this is needed to ensure integrity and authentication. So the three goals we talked about in the beginning: confidentiality, integrity, and authentication of the sender, okay. So these goals are achieved through message authentication code in symmetric key world. So basically there will be keygen tag generation and tag verify algorithm in a MAC, and for each message M, a corresponding tag T is generated, and that is in the sender end. So the sender will always send. So let's say your message is M, so it could be encrypted. So if we forget about the encryption first, so just say message M is being delivered, and integrity or authenticity is completely different concept than confidentiality. So if we don't care about confidentiality, we can send message M as plain text, and irrespective of the fact whether message M is being sent in plain text or ciphertext, you may want to ensure integrity of your message, and for that you will compute a tag T on that message, and you will send both your message M and tag T to the receiver, and receiver will verify whether the received tag T is indeed a valid tag of the corresponding message M that it receives by applying the tag verification algorithm, okay. And what is the concept of a secure MAC? So there are two kind of security defined on MAC. One is chosen message security, CMA security, or strong chosen message security, or SCMA security. So just as encryption scheme, where we talked about deterministic encryption algorithm and randomized encryption algorithm, here also the tag generation algorithm can be either deterministic or randomized. In case of deterministic MAC, the CMA security itself implies SCMA security. Why is that? So before that, let me just recapitulate what is CMA security. So the adversary here request for tag of its chosen message, say MI, and for every chosen message MI, it gets back from the challenger as response the tag TI for each message MI. Okay. Now, after seeing polynomial number of such message tag pair, the adversary's job is to come up with a new message tag pair. Let's denote it as M star comma T star, and adversary wins the game in case of CMA security if M star does not belong to MI, where I belongs to 1 to Q. Okay, for this whatever Q number of message tag pair it has seen previously. So its new message m star should not belong to any of this message in the query phase, and t star should be indeed a valid tag of m star. Then only we say adversary wins. And the MAC is secure if the probability of adversaries winning is negligible. And for SCMA or strong chosen message security, you have to ensure that the probability of adversaries winning is again negligible, but when adversary wins in this game, that is the whole pair m star comma t star should not belong to this any of the MITI pair for this Q number of queries. Okay. So why is that so? So basically, if I just said that for deterministic MAC, CMA security applies SCMA security, because in deterministic MAC, for each MI, you will have only one TI available because it is deterministic. So in case of randomized, for same message MI, you can have several possible tags, okay, in the tag space. So in that case, actually, your m star t star, even if m star belongs to some of the MIs in the query phase, your t star could be different of the corresponding TI in the query phase. And if your tag gen algorithm is randomized, then in that case, m star t star indeed will be a valid achievement by the adversary as coming up with a new valid message tag pair. So SCMA security is valid in case of randomized MAC, and in case of deterministic MAC, if it is able to satisfy CMA security, that is for a new message, it is able to come up with a valid tag, then that implies the so for any message m star which is not belonging to the query phase of any MIs, and adversary is not being able to come up with such valid tag of m star, then that only implies that m star t star also does not belong to any of these MITI pair of the query phase. Okay, so that is it. Now next we see the construction of MAC from PRF. So for fixed length message, using PRF, you can compute MAC as, so you generate the tag T as fk of m, where f is your PRF, k is the PRF key, also the same k is also said to be the key for the MAC algorithm, and m is the message that you want to be authenticated. Okay, then security of MAC relies on security of underlying PRF directly. Okay, and then for the MAC, for the tag generation of variable length message from PRF, you will have three-stage approach to construct PRF from PRF with arbitrary size input from PRF with fixed size input. If you are able to construct such PRF, then your MAC algorithm will also run accordingly for variable length messages. So you first construct blockwise prefix-free secure PRF, then you construct blockwise secure PRF. So this prefix-free restriction will not be there anymore. So what is prefix-free? What do we mean by blockwise secure prefix-free PRF? That is your PRF. So you were actually evaluating message blocks at a time. So there will be several blocks, each block with some particular length, and you are generating PRF for each such block. And the restriction is that when you are dividing your message into several blocks of same length, then those messages should be prefix free. Only in that case only the adversary is not able to distinguish the output of PRF from truly random function. Or in other words, the adversary is prefix free if it is querying the PRF, it is querying the oracle, whereas oracle can give it back the answer as PRF output or truly random output. In that case, the adversary is in that case, the adversary is not able to distinguish the output of PRF from output of truly random function only if your only if the query messages are prefix free. Means let's say you have two messages, M1 and M2, and M1 has message block as M10, M11, and M2 has message block M20, M21, M23, such that M10 is equal to M20. Okay, and if this happens, that means there are common prefix to both these messages. Okay, then this message space is not prefix free. Okay, so the first construction, blockwise prefix free secure PRF, is applicable only in case of prefix free adversary, and from that we actually proceed to construct blockwise secure PRF, where the restriction on adversary of being prefix free is not there anymore. And after that we proceed to constructing bitwise secure PRF, where the message need not be of any particular multiple of some particular block length, rather message can be of any length, and we can achieve bitwise secure PRF. So there are detailed discussion on the construction in the lecture itself. So next we talk about one-time MAC or information theoretic secure MAC. Okay, so we have seen in the normal MAC construction that adversary will query the MAC oracle for several messages of its choice, and it can see MITI pair for polynomially many times. But in case of one-time MAC, the adversary is allowed to see only one MAC evaluation of its choice. So it is seeing just M1, T1 for only one message M1, and after that its job is to come up with some other message tag pair M2, T2, such that it is indeed T2 is indeed a valid tag for the message M2. Okay, and this construction uses strongly universal function. This is another primitive where we say that H, which maps from key space K and message space M to tag space T, this is called a strongly universal function only if probability that Hk of M equal to T and Hk of M dash equal to T dash. Okay, these two are completely independent event of each other. That is the first event probability that Hk of M is equal to T, that will happen only with 1 by size of tau probability. So tau is the tag space, and the fact that T will be selected as the output of this strongly universal function, that probability is 1 by tau. And same goes for the fact that Hk of M dash will be T dash. Okay, because M and M dash are not related to each other, T and T dash also should be independent of each other and should be uniformly distributed over the output space, that is the tau. So 1 by tau size of tau square should be the probability of its happening. And so you can construct one-time MAC or information theoretic secure MAC from the strongly universal function. And here you allow the adversary to have unbounded computational power, but it is able to come up with valid message tag pair M dash T dash with negligible probability. So we call it information theoretic secure MAC. Next was this primitive cryptographic hash function. So hash function is many to one function which maps arbitrary length bit string to fixed length bit string, and collision resistance is one of the desired property for cryptographic hash function, which says that given the description of hash function which maps any length bit string to some fixed smaller length bit string, the adversary should not be able to come up with two such input x and y such that x is not equal to y, but h of x is equal to h of y. So that is the security for cryptographic hash function, which we call collision resistance. Okay. Now, how do we construct cryptographic hash function? So basically, if you have some fixed length collision resistant compression function. Compression function means which takes input of some length, say n plus small l, and compress the output to some smaller length. So let's say small n. So you had input of length n plus small l, and now you have output of length small n. So with such collision resistant compression function available to you, you can design collision resistant hash function for arbitrarily long messages. Okay. Remember, for hash function, your input space is arbitrarily long because we say that it's any length binary string. But in case of fixed length collision resistant compression function, your input length is fixed at n plus small n. So with such function available, let's denote such function as small h. Then how do you generate collision resistant hash function? So that is called Markle-Damgard paradigm for designing collision resistant hash function, and Markle-Damgard paradigm works as follows. So you will repetitively apply this collision resistant compression function small h sequentially. So you will divide your arbitrary length message into several blocks, each of length small l bits, because your compression function takes as input total n plus l length bit input, or you can see it as two input, one of length n and another of length l. So one input is coming from the message block, which each of them are l bits. So one input is coming from message block, and another input you can say as some initialization vector denoted as t0, which will have n number of bits. And having such n plus l number of bits as input, this compression function h will output some small n bits. Okay, and these small n bits output will be fed as input to the next stage of instantiation of this compression function h. And here again, another L bit of input comes from the next block of the message as shown in the figure. And like that it continues, and if it has S number of L size message block of the message, so the last block can be a padded block depending on the number of bits available in the message. Anyway, so MS will be also again L bit block, and the n bit input is coming from the previous stage, and such that the output TS will have again n number of bits. So overall you have the arbitrary length message M. You are converting it to some multiple of L length bits and dividing it into chunks, each of length small l, and you are applying this compression function small h again and again, and finally coming up with the output of hash function ts. And collision resistance of this hash function is depending on the collision resistance of the underlying compression function h. Now, how this compression function is designed? For that, we need Davis-Meyer construction, which is defined as h of dm for Davis-Meyer, and it takes as input one message of length L and your another input of length N T. Okay, and you apply basically a block cipher, which is also PRP, right? So if M of T, M is acting as the key of the block cipher, which has length L, and T is the input to the block cipher, which has length N, and with n bit length input, the PRP will output again another n bit output only, and with that you XOR this n length T again, and Fm of T plus Fm of T XOR T, that is the construction of Davis-Meyer function. Okay, so this construction is collision resistant compression function in ideal cipher model. So ideal cipher model is not its standard model where we just assume the pseudo-randomness of the output of block cipher. Apart from that, we also assume that here the adversary has oracle access to F and F inverse. That is, the adversary can query the oracle with the value of M and T, and it just gets as output the value of F of T for key M. And also the oracle can reply to inverse query from the adversary as well. So for some output, say Y, under the key K, it will reply back with F inverse of Y with respect to key K. And when we say it's an oracle access, then it is assumed that the underlying algorithm of the block cipher F is hidden to the adversary. It is just accessing the value of the or output of the block cipher. And with this assumption in ideal cipher model, this Davis-Meyer construction is collision resistant, and of course it is a compression function. Okay, and using such compression function, you can further apply Markell-Damgard paradigm to design collision resistant hash function. Okay, so we also studied about the concept of authenticated encryption. So we said, by the way, there was also constructions of block ciphers. So there are concepts about how we can use PRP as block cipher. There are several modes of operations of block cipher. We have seen them, like ECB mode, CBC mode, output feedback mode, and all. So we had discussed about various problems on those also. So you can take a look at them also. Well, we also discussed about DES and some of like overview of the AES constructions, which are heuristically secured and which are used in real life as block cipher. Okay. So, okay, then we come to authenticated encryption, where we actually achieve all the three goals of confidentiality, integrity, and authentication. So, authenticated encryption scheme will satisfy the concept of CCI security and ciphertext integrity both. So, what is meant by CCI security, that we already discussed in the beginning. And what is ciphertext integrity? So, formally, let's say an adversary provides message of its choice to the challenger, and in response, challenger gives the corresponding ciphertext. So it's just encryption oracle access to the adversary, and then the adversary should be able to come up with a new ciphertext C star such that C star decrypts in a valid way. That is, decryption of C star under the same key K should not be bought or invalid message. So it should be a valid message in the message space, and also M star should not belong to any of the previously seen messages by the or previously sent messages by the adversary. All the MIs are chosen by the adversary itself, but adversary should be able to come up with some ciphertext C star such that it decrypts to a valid ciphertext M star in the message space, and the decrypted message M star should not belong to any of the previously sent messages MIs. Okay. If adversary is able to do that, then adversary wins. But of course, to ensure ciphertext integrity, we need the adversary to have winning probability negligible. Okay. Now, that is the concept of authenticated encryption, and then we proceed to public key paradigm. So in public key paradigm, as you know, there will be concept of two keys, public key and private key or secret key. So we talk about several number theoretic assumptions here to build our construction upon them. And we had seen this discrete logarithm problem where you have a publicly available group description. This group should be cyclic group, and by cyclic group we mean that there has to be one or more than one generator in a cyclic group, such that for these generator elements, if you apply your group operation on this generator element multiple times, and you are able to get all the group elements one after another for several number of times applying the group operation on this generator G. So that means g to the power 0, if G is the generator of group capital G, small g is the generator of the group capital G, then small g to the power 0, small g to the power 1 till small g to the power q minus 1. This is nothing but a permutation of all the group elements in capital G. And q is here the size of the group or order of the group also. So in such a group, if your challenger provides the adversary with some arbitrary group element q, of course, u can be represented as g to the power alpha for some alpha belonging to 0 to q minus 1. Then the adversary's job is to come up with the exact value of alpha. Okay. So the adversary returns some group element alpha dash in response, and adversary wins if alpha dash is equal to alpha. That is so discrete log assumption says that this problem is hard to solve for any polynomial time adversary. Well, I should just mention for the sake of completeness here. So all the adversaries we assume in computational secrecy model is probabilistic polynomial time adversary. That means the it is polynomial time adversary. That means its computational time is bounded. So it should not run for infinite time. It should run its algorithm to attack the crypto system in polynomial time only. So it should be polynomial time adversary, and by probabilistic we means the adversary uses randomized algorithm in order to attack the crypto system. So in short, we say the PPT adversary, probabilistic polynomial time adversary. Now, coming back to this discrete log problem. So the candidate groups where it is believed that solving discrete log problem by any PPT adversary is hard, then we say that in those groups discrete log assumption holds true. And there is another problem related to this discrete log problem, which we call computational Diffie-Hellman problem. Here, the challenger actually sends adversary two group elements for the group capital G. And let's say these two elements are u and p, and u must be g to the power alpha for some alpha in 0 to q minus 1, and p must be g to the power beta for some beta 0 to q minus 1. And in response, the adversary is supposed to say send another group element w such that w is g to the power alpha beta. Okay. Again, the computational Diffie-Hellman assumption or CDH assumption says that for proper candidate groups, this coming up with correct W is hard for a PPT adversary. And another problem is DTH or decisional Diffie-Hellman problem. Here, the challenger sends a triplet to the adversary. Triplet is of the form U, V, and W, where U is of the form g to the power alpha, V is of the form g to the power beta. Of course, alpha beta belongs to 0 to q minus 1. And W can be either of form g to the power alpha beta or of the form g to the power gamma, where gamma is some random element of 0 to q minus 1. And seeing such triplet UVW, the adversary needs to distinguish whether it is seeing a Diffie-Hellman triplet or not. So Diffie-Hellman triplet UVW will be called Diffie-Hellman triplet if W has the form g to the power alpha beta, otherwise not. So adversary has to distinguish these two scenarios between Diffie-Hellman triplet and random triplet of the space G. Okay. So adversary here also wins if B dash is equal to B, and DDH assumption holds true for the candidate groups where decisional where DDH problem is hard to solve by any PPT adversary, and uh, DDH problem is comparatively easier to solve. So DDH assumption is a stronger assumption than CDH assumption. And similarly, if you are able to solve DL discrete log problem, then you will obviously be able to solve CDH problem easily. So CDH problem is probably comparatively easier than the discrete log problem. So CDH assumption is stronger assumption than discrete log assumption. Okay. Also, so the candidate cyclic groups where these assumptions, that is discrete log assumptions, computational Diffie-Hellman assumption, and decisional Diffie-Hellman assumptions hold. So there are two such candidate cyclic groups. One is prime order cyclic subgroup of ZP star. So ZP, actually it should be ZP star. So ZP star is cyclic group under multiplication modulo P, and if we take some subgroup of ZP star of prime order Q such that P is equal to RQ plus 1, and we form the subgroup is of the form H to the power R mod P such that H belongs to ZP star, then such a subgroup is believed to have all these three assumptions satisfied in it. And another candidate cyclic group is the additive group of points on elliptic curve modulo some prime. Okay, elliptic curve has this specific structure. It satisfies this equation y square equal to x cube plus ax plus b for some a b modulo p. So we have discussed about elliptic curve points and their behavior, the addition operation, the identity element inverse, etc. Previously. So anyway, and there is construction of Ilgamal public key encryption, where you know that description of the group, that is G, capital G, the set of elements, the operation dot defined on the group, Q, the size of the group, which is a prime also, it's prime order group, and the generator small g. So these are part of the group descriptions which is available publicly, and then alpha belonging to 0 to q minus 1 is some secret key chosen, and g to the power alpha, which we also denote as h, is kept as the public key. And then encryption occurs as follows. So encryption of some message m belonging to the group G will have the ciphertext of the form C1, C2, where C1 is so the sender or the encryptor chooses some beta belonging to 0 to q minus 1 randomly, and then it computes z to the power beta, and that is the first component C1 of the ciphertext, and the second component of the ciphertext is computed as M0 dot h to the power beta, where dot is the group operation, h is the public key. So h to the power beta is nothing but, if you see, g to the power alpha beta. So that is kind of the common key that they want to use for communication. Okay, so I actually just missed the Diffie-Hellman key exchange above. So you already know, right? So Diffie-Hellman key exchange is used for exchanging a or for deciding a particular key between two parties. Okay, all the symmetric key primitive we had seen. So there, both the parties communicating with each other had this secret key previously shared among them, using which they encrypt, decrypt, and all. But how they agreed upon such a shared key K, that was not clear previously. So that's why we talk about the key exchange problem, and Diffie-Hellman suggested this nice idea of exchanging a key or sharing a key between two parties even without any prior information between them. So Of course, the group description is publicly available, but then the two parties A and B, each of them individually chooses their own secret alpha and beta from the space 0 to q minus 1, and A sends g to the power alpha through the public channel to B, and B sends g to the power beta through the public channel to A. Okay, and then A, upon receiving g to the power beta from B, will raise that element to the power of alpha. Okay, so v to the power alpha is computed, which gives nothing but g to the power alpha beta, and B also, upon receiving u, which is g to the power alpha from A, it will receive u to the power, it will compute u to the power beta, which is nothing but g to the power alpha beta. So both of them agree upon this key g to the power alpha beta. Okay, so that is how key exchange occurs, even though they did not have any prior information shared between them, but they still agreed upon the same key g to the power alpha beta, and also by the computational Diffie-Hellman assumption holding true for that particular group. In the public channel, although some adversary is able to see g to the power alpha and g to the power beta individually, it should not be able to compute effectively with except with negligible probability the value of g to the power alpha beta. Okay. But this key exchange protocol has this limitation that k is just a group element. So you should be actually able to come up with any uniformly random looking string as the shared secret between the two parties, but it is restricted to be some particular group element. So you can apply, after calculating g to the power alpha beta, you can apply some key derivation function on that key k. Key derivation function we talked about while discussing the application of hash function and all. So anyway, so that is one limitation of Diffie-Hellman key exchange protocol. And then Diffie-Hellman key exchange protocol is not secured against active adversary. Okay, so there is man in the middle attack and all. So it is not used in real life in its naive form. You have to make necessary changes for that. And then we come to Elgamal public key encryption, where we have just saying that the encryption or the ciphertext has two components, C1 and C2. C1 introduces the amount of randomness required for randomized algorithm. So beta is the randomly selected value between 0 to q minus 1, and C1 is computed as g to the power beta, and C2 is computed as m dot h to the power beta, where h is the public key. The public key is h here actually. So you raise h to the power beta, which is nothing but g to the power alpha beta. That is the agreed upon key between the two parties, and with that key you apply the group operation on m. Okay, and while decrypting, so you first compute the common key k by doing C1 to the power alpha. Note that C1 is nothing but g to the power beta, and raising it to the power alpha gives us g to the power alpha beta, which you can also write as h to the power beta, and your component C2 has the form m dot h to the power beta, and with that if you just again apply the same operation h to the power beta on it, so you will be left with the message m only. So that is how you retrieve message m. Okay, or maybe I think okay, it should be h to the power beta of inverse, because if you are dealing with group with some group operation dot, then actually h beta dot h beta inverse will give you the identity element, and then m dot identity element give you m. So this should be inverse actually. Okay, so you can retrieve m. And remember, exponentiation operation is not a costly one, and it can be done publicly in a prime order group. And each element has its multiplicative inverse in prime order. Okay, so that is how Elgamal public encryption scheme works, and it is, as you know, it is CPA secure because there is it has randomized encryption algorithm, but it is not, of course, CCA secure. You can show malleability of its ciphertext, and hence CCA insecurity of PKE. There is another assumption, number theoretic assumption called the RSA assumption. So here the public key encryption works as follows. So you choose two large prime P and Q of similar bit length, and then you compute capital N equal to M P into Q, and then you choose E such that GCD of E and phi N is 1. Phi N is the Euler-Thomson function, that is number of elements in the set Zn which are co-prime to N. That is the and the number of elements in that set is denoted as phi N. And you choose such E, and then because E is co-prime to phi N, you can find inverse of E modulo phi N, and you denote it as D, and then you output N comma E as the public key and N comma D as the secret key. And encryption works as encryption of some message X is computed as X to the power E mod N, and then decryption of some ciphertext Y is computed as Y to the power D, where D is part of the secret key. So Y to the power D mod N is computed during decryption. That is the very nice, very naive version of RSA algorithm. However, this RSA algorithm, as you can see, the encryption algorithm is deterministic, so it is not providing the least security requirement, which is the CPA security. So it does not provide CPA security, and of course neither CCA security as well. But you can modify this RSA encryption scheme by using various other techniques. So we discussed about padded RSA and also you can modify it to make it CPA secure, to introduce some randomness in the message. Okay. So we also discussed about several attacks on RSA, like no message attack, arbitrary message attack, and all. We also discussed malleability of Ilgamal ciphertext. Also, just a point to remember, for any public key encryption scheme, COA security implies CPA security, which is not the case for symmetric key encryption. Because in symmetric key encryption, the adversary is required to explicitly give access to some encryption oracle, whereas in case of public key crypto system, the adversary itself has the access to public key PK, which is also the encryption key. So the adversary can use the public encryption key to see the see any number, see ciphertext of any number of messages of its choice. So it need not explicit access to encryption oracle. So in any public key crypto system which is ciphertext only attack secure, COA secure, that is by default CPA secure as well. Okay. We also discussed about the concept of key encapsulation mechanism. So key encapsulation mechanism, or KEM, consists of three algorithms: keygen, encapsulation, and decapsulation algorithm. Keygen again outputs two keys, one public key and one secret key. Encapsulation makes use of the encapsulation actually makes use of secret key SK, okay, and it encapsulation makes use of some key PK, okay. And it samples some random symmetric key K from the symmetric key space, symmetric key encryption algorithms key space, and then it encapsulates that key K with public key PK, okay, and then it just sends the encapsulation of key K to some other party, and that other party will decapsulate using the secret key and recover the underlying symmetric key, which will be used further in the next phase of the communication, uh, which will be continued in the symmetric key setting. So usually in when we communicate in the real world, the public key encryption system being very computation heavy, it is just required during the key exchange phase, where using public key setting, the two parties communicating are agreeing upon some fixed key k, and that symmetric key k will be used further for further communication between, because symmetric key encryption symmetric key setting is lightweight while communication. Okay, so that is what the concept of hybrid public key crypto system also. So we discussed about identification scheme, which is again used for authentication. So there is some entity who wants to prove its identity to some verifier. So scheme between prover and verifier, and usually it consists of 4 algorithms: keygen, P1, P2, and V. P1, P2 are prover side algorithm, and V is the verifier side algorithm. And so then from identification scheme, we also talked about how to so identification scheme is usually interactive scheme consisting of this commit, challenge, response, 3-round interactive protocol. And then from that, using fiat semi transform, you can actually get non-interactive 1-round digital signature scheme. What is digital signature? That was also discussed. This can be thought of public key version of message authentication code. MAC is also used for ensuring integrity and authentication of the message and the sender. And digital signature scheme also uses this public key secret key setting. So while signing a message, the signer will make use of its secret key, and the signed the signature is actually publicly verifiable. So you sign a message M with signature sigma, and that signature sigma is indeed a valid signature on message M that can be verified with the public key of the signer. So that verification can be done publicly. So there is a difference between MAC and digital signature in terms of public verifiability. So MAC can be verified only by the intended party who has the access to MAC key K, right? So only two parties who are sharing information with each other using the MAC key K, they are only able to verify each other's MAC tag. But in case of public key primitive digital signature, there once a signer signs a message using its own secret key SK, then anyone in the system who has access to this signer's public key, it can verify the signature of that message. Okay. Also, it satisfies the non-repudiation problem. So any sender, if it once signs a message with its own secret key, it cannot deny afterwards that it has not indeed sent the message, because the verification can be done only using the verification key of that signer itself. Otherwise, it is not verifiable. So if it is verified using your public key, then you are actually the sender of that message, not anyone else. But in case of MAC, the MAC key K is shared between both the parties, sender and receiver. So if a MAC tag is generated corresponding to some message M, then that tag can be computed by both the sender and receiver. So who actually generated that tag cannot be determined afterwards, right? So this is another advantage of digital signature over MAC. So anyway, and what else? So there was, we also discussed about secret sharing schemes, additive secret sharing, replicative secret sharing, and also this semi secret sharing scheme, which is nice and efficient design of secret sharing scheme. And then lastly, we also discussed about zero knowledge proof, where a prover proves that it acquires some secret information or some confidential information to a verifier without giving out any meaningful knowledge uh, about the secret information to the verifier. So that is what is the concept of zero knowledge proof. So all over there are quite a very quite details of all these primitives and schemes that we discussed throughout this course. So I just tried to touch the broad topics today to give an overview, and so that is it for today. And thank you very much for joining the session, or whoever is following the live session videos. And okay, all the best to your exams. Okay, thank you.